So it's a great pleasure for me to introduce our today's speaker, Professor Alexei Kitaev. So Professor Kitaev got his PhD from the Landau Institute for Theoretical Physics in 1990, and he spent a decade as a member of that institute, and then moved to the US, first as a member of the technical staff at IBM, and then starting with 2002 as a professor at CalTech. First, he was a professor of physics and computer science, but more recently, Professor Kitaev changed his affiliations, and now he's a professor of physics and mathematics there. Now, these titles actually reflect the fact that our today's speaker is unusually distinguished in all three fields of physics, mathematics, and computer science. And this was recognized by numerous major awards, including the MacArthur Genius Award, the Fundamental Physics Prize, the Dirac Medal in Theoretical Physics, and most recently, this year's Oliver Buckley Prize from the American Physical Society for the outstanding contributions to solid-state physics. I think at this point I need to stop listing the awards by our today's very distinguished speaker, because I need to leave some time for the talk. But there is one small award that I always love to mention. So in 1997, Professor Kitaev won the first place at the competitions of science works at the Landau Institute. And I always love mentioning that because I got the second place that year. Now, another thing that I really love to mention, and I mentioned that actually at the colloquium delivered by a co-author of our today's speaker, but this story that I really love to tell, especially to undergraduates, is the story of his very first paper, which was co-authored by him with two other undergraduates, the same age as our seniors. And that was a completely groundbreaking paper in crystallography. So in middle 80s, a very strange experiment was published by Dan Schachman, who went to win a Nobel Prize in Chemistry for that work, when he saw that certain crystals made of aluminum and manganese were symmetric with respect to rotations by 72 degrees. Now you will tell me, so what? 72 degrees. But everyone who took an elementary solid-state physics class knows that allowed symmetries include 60, 90 and 120 degrees. You cannot have such symmetry in a crystal. 72 degrees is prohibited, and making sense of that was extraordinary challenge. The solution was found in a highly unusual paper with highly unusual title by three undergraduates from the Landau Institute. The title is actually Aluminum Manganese is a 6-dimensional crystal. So I highly recommend reading this paper. An undergraduate can understand it. In fact, an undergraduate can make that, as our today's speaker illustrates. But then he actually didn't continue working in crystallography, and instead went to many other fields, publishing work on spin glasses, on mathematical logic, on quantum chaos, and later on quantum information, where Alexei Kitaev made a lot of very important contributions. One of them is particularly well known. I suspect that most people in this audience heard about the idea of topological quantum computing. But perhaps even more importantly, our today's speaker made some very major contributions to the field of topological states of matter. One example is three famous exactly solved models, the toric code, the Kitaev chain, and the Kitaev model, that turned out to be both simple enough to actually allow an exact solution, but still complicated enough to shed enormous light on the very nature of the topological order. And then, as I mentioned, our today's speaker really is someone who works in very many fields, even beyond physics. As one more recent example of that, I can mention his outstanding work in the intersection of physics and mathematics, his periodic table of topological insulators that brought together one of the most important achievements in 20th century mathematics, the K-theory, and one of the most important achievement in the 21st century physics, the discovery of topological insulators. Yet our today's talk will have nothing to do with any of these topics. It's not about topological insulators, it's not about quantum computing, it's not about crystallography. Today we'll learn about black holes. So please welcome Professor Kitaev here.
Thank you, Dima, for the introduction. It's a pleasure for me to speak here. I'll talk about this toy quantum black hole, a toy model of a quantum black hole, and just adding a little bit to Dima's introduction so that it doesn't sound too complicated what I did. I just played with various toys in each of these fields. I just tried to solve the simplest possible problem. and they are still interesting, but they're simple. So you can do many of them pretty easily. This one is actually slightly more complex. It has more equations, which I won't bother you with. I'll just talk about qualitative stuff and the introduction. So, oops. I don't know what happened. So my slide doesn't. Oh, good. The ultimate goal of this work is to approach a quantum theory of gravity. Of course, it's the holy grail of theoretical physics. I'm not going to solve this problem myself. Just let me remind you what the problem is. If we think about gravity, it usually shows up at large scales, and quantum mechanics is important in smaller scales. But if we go to this range of distances, a very small distance and very large energy, then quantum fluctuations of space-time will be important. And it's not yet understood what happens at these small scales. Gravity cannot be quantized in the usual way. Usually, if you try to deal with the divergences that occur, you face very serious problems. And there is a reason to believe that space-time becomes non-local, or interactions in space-time become somewhat non-local, and you need some extended object to deal with that. String theory provides such extended objects, string loops, but this is a complicated theory, and it's just too complex for me to understand. In this talk, I'll try to do something simpler, but it might be the ultimate quantum theory of gravity. It's not complete yet. So I will try to just say something qualitative about quantum gravity without constructing an actual theory. So this is an observation. If we try to approach this quantum limit from the classical side and do semi-classical theory, there are some quantum effects that show up, for example, in the black hole radiation, which was discovered by Hawking more than 40 years ago. And this is certainly a correct result, but it leads to some paradoxes. And it would be nice to find a quantum model that reproduces this basic semi-classical result and other semi-classical results. But being fully quantum, it should give definite answers to those paradoxes. And I'm going to present such a model. I don't know those answers to the paradoxes yet, but it's still an exciting question. The key step will be to look carefully at black holes and quantum fluctuations in black holes. Although these are weak fluctuations and can be treated semi-classically, they show some universality. And this universality occurs, it exists in so-called out-of-time order correlators. To measure such a correlator, we need to be able to go back in time. So imagine that we have a toy black hole in a little box. We can put it in the box so that to prevent it from disturbance from outside. And there is a switch. We flip the switch once, one direction, time goes forward. The other direction, time goes backward. And we go back and forth in time and do some measurements. And this kind of measurements is needed to detect the special correlators that are universal for black holes, that set black holes aside from other systems. The model I'll describe will be 0 plus 1 dimensional. It's just quantum mechanics of a system with many degrees of freedom, but it doesn't have any space, only time. And it corresponds to a gravitational theory in one spatial direction and one time direction. This is the model, and I'll explain it to you again. Just very quickly, let me tell you what the ingredients are. There are n Majorana modes, these green dots. Each green dot is a site that contains half of a fermion. Two sites together would make a fermionic mode in the usual sense, which is described by a pair of operators, a creation operator and an annihilation operator. And those chi operators are just linear combinations, either A plus A dagger or A minus A dagger. And this is a nice algebra, it's called Clifford algebra, of operators and n Majorana modes, where n is even, have 2 to the n over 2 basis states. This is the Hilbert space that has dimension 2 to the n divided by 2. And in this Hilbert space, there is a Hamiltonian with interactions. It's a fourth order interaction. If it were a quadratic interaction, it would be easy to solve, and it's just a linear algebra. We would need to find the spectrum of the matrix. But in this case, it's a fourth order interaction, so it's more difficult to solve. Still, the model is solvable in a certain sense using dynamic mean field theory. And this model is based on an earlier model by Sage-Definier, who considered SUM spins and used a certain representation of those spins. This is a more complex model. My model is a simplification of that, but the basic features are the same. So one can define green functions. The key simplification of this model is that disorder effects are small, because this model has many variables, these random couplings. And since there are many small random variables, they add up together and make an almost Gaussian variable in some abstract sense. And this is why fluctuations between different realizations of disorder are small in this particular model. And the model has an emergent conformal symmetry and a pseudo-Goldstone mode. I'll explain that. And I actually never published a paper about this model, but I gave several talks, and Maldacen and Stanford did the hard work and calculated all the correlation functions, and they wrote a very nice paper. So let me begin with the basics. It's an introduction about black hole. Of course, black hole, as we know, it is a big object that sucks everything. And it's a pretty old idea that a large body will have such strong gravitational field that nothing can escape. One can estimate the escape velocity using non-relativistic physics by just saying that the potential energy in the gravitational field of a body with this little m mass, little m, plus the kinetic energy is 0, and this gives this answer for the radius of the black hole if we plug the speed of light instead of v escape. It's actually an exact answer for some reason, although it's supposed to be an order of magnitude estimate. And when we go to general relativity, we use the correction to the time rate. The proper time differs from the lab time from some other time by a factor that depends on the gravitational potential, the first line is an approximate relation, and one can also read it in this way, that this gravitation change of the time rate creates a potential energy that is proportional to mc squared, and that's why a tiny change in the time rate corresponds to a large potential energy. And the actual change in the time rate for black holes, spherically symmetric black holes, is given by this formula. It's this A over R, so that you can easily recognize it, is the same as this 1 over R in the Newton's formula. And if we not only include the time but also space, we'll get this metric, Schwarzschild metric, that has the same function f, this 1 minus a over r, in two places. One multiplies dt squared and the other multiplies dr squared. So the time rate is multiplied by f, and spatial distances are divided by f. Now, one important thing to understand about black holes, which is necessary to quantize them, is that the apparent singularity at r equals a is not really a singularity. It's just an artifact of this coordinate system. So if we consider just the usual two-dimensional Euclidean space and write it in different coordinates, use coordinates w and phi, like the polar angle, and rewrite the standard flat metric in these new coordinates, it will appear as singular. It will have w in the denominator. But we know it's just plane. We can do the same with the Minkowski space and introduce this Rindler coordinate. We can use x0 and x1 as functions of t, time t, and some radial coordinate w. This square root of this combination is not so important, but it's if this prefactor is fixed and only time changes, we get a green curve that corresponds to a body that moves with constant acceleration given by kappa. So in this case, the length element also looks singular, but we know that it's just a flat space, and this coordinate grid in the TW coordinates only covers a wedge 1/4 of the actual space. And for the black hole, it will be the physical wedge, where things behave in a normal way, but there will be other places. So if we go to the black hole geometry, this is a so-called atonal black hole. It has a physical wedge that is covered by the Schwarzschild coordinates, and the Schwarzschild coordinates r and t are mapped in here, but there are other places. This is the full picture. The physical wedge is here. An overly curious observer may actually go to other places, but if the observer crosses the future horizon, there is no way back. And in a short time, he will hit the singularity and die, because this is the end of space-time. And in this picture, there are 4 wedges, but that thing on the bottom, the very bottom part and this part, do not occur in real black holes, because along this line, the solution on top should be glued to a different solution, because this line represents the trajectory of a collapsing star. And the space-time before the collapse should go there in this region. So it's called eternal black hole because it's a black hole that was never formed by collapse. It existed for infinitely large negative times. And it's believed that such black holes will have properties very similar to real black holes. Now, let's talk about some quantum effects in black holes. The basic effect is Hawking radiation. Black holes emit radiation quanta, photons, and other particles. And this picture shows that near the horizon, there are many particles that are being emitted and fall back. These particles of different color. At larger distances, there are fewer particles, and only a few particles escape to infinity from the black hole. The horizon is actually very hot. There are many particles, but most of them are trapped. Now, technically, the calculation goes this way. We need to calculate the correlation function of some field, say the electromagnetic field or a free fermion field or a scalar boson. And the physical wedge can be solved by using a Cauchy problem. We put some Cauchy data here on the past horizon and propagate it forward. And given this data on the past horizon, we can always propagate and find everything. But how do we know what the correlators are on the past horizon? We can make an assumption that the correlators on the past horizon are similar to vacuum correlators. If we make this assumption, then we can calculate the correlation point of two fields at x and y. And let me show you how it works. For a free fermion field, the vacuum correlator on this line on the past horizon is given by this formula. It's proportional to u minus u prime to the minus 1. U is the coordinate along the past horizon. And this is a vacuum correlator for a free fermion with zero mass propagating to the right, this little arrow. Then we just say the global time t is a new coordinate that is related to u by this equation. It's just a coordinate change. We apply that coordinate change to this function and we'll get a new function. And miraculously, this new function is the correlation function of a free fermion at finite temperature. Beta is the inverse temperature. Just by this coordinate transformation, we get a finite temperature. Hawking obtained this effect by a slightly different way. He actually considered the black hole collapse, but this is also a legitimate way to do that. And there is a relation between beta and parameter kappa. This parameter kappa I introduced last time. I didn't mention this important form. This parameter goes back here. It's the acceleration. And for black holes, it's called surface gravity, the acceleration of gravity at the gravitational radius. It's the ratio of the Lorentz boost at the horizon and time at infinity. Because as we do a shift in time, it's so-called Killing vector. We shift in time at infinity by a constant, but at the horizon it's making a Lorentz boost, and the ratio is called surface gravity. So there is a relation between the surface gravity and temperature, and this is a fundamental relation derived by Hawking. Its quantum effect H bar is here. Hawking also made a qualitative description of entanglement between different photons or other particles. According to his picture, particles that are emitted by the black hole, these red particles, they enter the physical part of space through the past horizon. They are entangled with these green particles that will hit the singularity. So there is a perfect entanglement between each green arrow and each red arrow. This green arrow is entangled with that red arrow, and the arrows on the opposite sides are also entangled. This is according to Hawking. Now, Bekenstein conjectured, and Hawking actually showed using his results about radiation, that black holes have entropy, and this is a huge entropy. If we imagine planet Earth, it's a body of this mass, collapsing to a black hole, it will make a very small black hole of radius about 1 centimeter. And the entropy is proportional to the surface area of the sphere divided by 4 times the Lp squared, the Planck length. And this is the number, 10 to the 66. It means that this black hole has that many quantum degrees of freedom. And if we could control it, we could store 10 to the 66 bits of quantum information in the black hole. And the derivation is nice and simple, but also somewhat obscure, because it combines some classical physics, the Schwarzschild radius, the surface gravity, these are all classical quantities, the Hawking formula, which is quantum, it's quantization of fields in the curved space, and if we combine them, we can compare two classical relations. One relation is in general relativity, is the relation between the energy, the horizon area, and surface gravity. It's a general relation, but you can check it using these numbers for the Schwarzschild black hole. And this equation looks very similar to the first law of thermodynamics, written as dE equals TdS. And we can just make one-by-one correspondence. And area will correspond to the entropy with this coefficient. The derivation is semi-classical. It gives no clue what the microstates are. We know that there are 10 to the 66 degrees of freedom, but we don't know what they are. And we'll try to understand that using some model. Of course, in the real world, it can be different, but I'm going to propose a model. So these are some related ideas, which are bigger. These are not toys. Black holes provide the densest packing of information, and it's strange that the information is limited by the area rather than volume. Hoof conjectured that this is not an accident. That's because there are some degrees of freedom on the horizon. On any surface, there are degrees of freedom that are equivalent to anything that is in the bulk, that is enclosed by that surface. So there is some alternative description, but he didn't say what that description is. And Maldacena found an actual model where such a correspondence exists. It's some supersymmetric Young-Mills theory and string theory in anti-de Sitter space, something rather complex. This is a very deep conjecture, and since on both sides, both on the surface and in the bulk. We have theories that are hard to solve. One can only calculate certain things and make a comparison between those things. But so far, everything has agreed between the two sides of the calculation. So there is strong evidence that these two theories are actually equivalent. There are also many extrapolations which roughly say that anything, it's a very strong extrapolation would be to say that anything on the surface has a dual bulk description. But it turns out that in some physical systems like quark-gluon plasma or strongly correlated electron systems, one can make predictions using those extrapolations, and those predictions look reasonable. They may not be quantitative, but qualitatively they are correct. So I would like to understand what's going on and make some quantitative model. Maybe it won't have the full power of Moldasena's model, but it will be simpler. Now, my starting point to make such a model will be the black hole information paradox. The paradox is about where information goes when something falls into the black hole. And on the one hand, according to Hawking, when something falls into the black hole, then the black hole entropy increases, the energy increases, and then the black hole can give out this energy by emitting radiation. The radiation quanta will be thermal. And one can argue that not only each particle has a thermal distribution, but their distributions are independent. And the argument uses some properties of quantum mechanics, so-called monogamy of entanglement. In classical systems, it would be possible to make correlated radiation quanta such that each one has a thermal distribution. In quantum mechanics, if we assume that each particle that goes out has an entanglement partner that remains inside, then any correlation between the outgoing particles becomes impossible. Because if we have particle A perfectly entangled with particle B, A and B form a pure state. And if there is a third particle, C, this is a perfectly entangled state, an example of such a state. If we have another particle, C, then the joint state of all three systems is just the tensor product. We have A and B that are in a pure state, and C is completely uncorrelated with A and B. So if Hawking's picture were exact, there would be no correlations between the thermal quanta. However, if we make a black hole out of some pure state of particles and let it evaporate, it should be back to a pure state because quantum mechanics is unitary. So there is a contradiction. And the resolution is not obvious. And actually, Hawking and Preskill made a bet a long time ago. More recently, Hawking conceded. And it seems that information is preserved. It doesn't disappear in the black hole. But still, it's not completely understood how it comes out. The exact mechanism is not known. And it would be nice to understand. I don't know that either, but I'm trying to approach this problem from one particular side. One possible mechanism that produces some correlations in the black hole radiation was proposed by 't Hooft. And 't Hooft noticed that if there is an incoming particle, something would drop a rock to the black hole and wait. And suppose sometime later radiation comes out of the black hole. Then this infalling rock and the outgoing radiation will meet at very high speeds. They will be Lorentz boosted relative to each other, and this Lorentz boost grows exponentially in time. They might not collide head-on, but the incoming particle would produce some gravitational perturbation, and this gravitational perturbation would look like a shock wave concentrated on the past horizon. Any particle that goes out, say a light particle, would shift in time as it crosses the shock wave. It's not an actual singularity. Again, it's an apparent singularity that can be removed by a coordinate transformation. But the effect is still there. Anything that comes out experiences some shift along the past horizon. And if we consider quantum effects of such shifts, then we can find some correlation in the outgoing radiation. But here is the crucial point. We can try to measure some observable staying in this region. If we measure any observable, these shifts don't make any difference because the quantum state on the past horizon as a whole remains invariant. The only way to see those correlations is to correlate something outside and inside. So on this side and on that side. But we can never enter this place. Or maybe we can. We could enter this place if we could travel back in time. And such as this observable, it's called an out-of-time order correlator. We go and measure a product of operators, A of 0, B of t, C of 0, D of t. And this way, we effectively cross this line just by constructing this correlator. This is a mathematically defined quantity. For any quantum system with a Hamiltonian, we can define such a thing. Let's talk about different types of correlators. There are naturally ordered, so-called Keldysh correlators, and out-of-time order correlators. A Keldysh correlator is defined for a system interacting with a probe. So there is a separate Hamiltonian for the system, the probe, and the interaction. And the observable x sub j acts on the system, and this observable acts on the probe. If we calculate the probability of some outcome, it looks complicated, some time-ordered exponential, and so on. If we expand this exponential, we get products of operators, but the important feature is that the times that occur in this expression go up and then down. And this is called the Keldysh contour, Schwinger-Keldysh contour. Schwinger also considered it. Times go up and then go down as we read off the sequence of times from this expression. Formally, one can define out-of-time order correlators on any contour that makes any number of terms. And this is the simplest one that does not reduce to this. Out-of-time order correlators were considered by Larkin and Ovchinnikov back in 1969. And classically, they describe the divergence of trajectories of points in the phase space, like the coordinate and momentum of a classical particle. If we have a chaotic system, we can start with two nearby points and evolve the system forward in time, and this evolutions will diverge. And this is well-known butterfly effect. A flap of a butterfly wings can change the weather if we track the perturbation. So if we compare the perturbation, if we compare the weather that would happen, say, a month later, with the butterfly present and without the butterfly, they would be different. A tiny perturbation to the system might change the outcome. Of course, to us, both outcomes would look random, so it wouldn't make much a difference. But theoretically, if we could simulate both processes, we would see the difference. Another way to see the difference is by so-called Loschmidt echo. So it goes back to the 19th century. Loschmidt criticized Maxwell's derivation of the H theorem. The H theorem says that the entropy increases in time if we solve the kinetic equation. And Loschmidt's argument was that if we reverse the direction of all molecules in a gas in a box, then the entropy would decrease. In principle, if we have a closed system and we have full control, then indeed the system would go back. And we can imagine a process by making a scrambled egg. We just break the egg, it's in the frying pan, and if we can reverse the evolution, it will become again a whole egg. If something happens, the tiniest perturbation, like absorbing a single photon or something even lower energy perturbation, an arbitrary change in the quantum state, chances are that the egg will not reverse the evolution, it will remain in the frying pan. Any smallest change will mess things up. This out-of-time order correlator quantifies the sensitivity of the system to such perturbations. So this would be the experiment an experimentalist would need to do to test some predictions about out-of-time order correlators. But theoretically, actually, some experiments are done, and more experiments are discussed. They are usually done in small systems, like molecules, NMR in molecules. This is one way, and there are also attempts to do it in quantum optics. But at short times, the deviation of this correlator from the trivial correlator grows exponentially, but it starts out small. N is the system size. It starts out small and soon becomes big. This exponent, kappa, the growth exponent, is always smaller than 2 pi t, and that was proved by Schenker, Stanford, and Maldacena. This growth exponent will be the universality feature that is used for the construction of the model. So if we calculate the out-of-time order correlator in 't Hooft setting by sending shock waves, these shock waves are sent by apparatus A and C and measured by apparatus B and D, and this is a well-controlled system like black hole in a box. And the growth exponent happens to be exactly 2 pi t. Now, kappa has two meanings in this case. On the one hand, kappa is the growth exponent defined on the previous slide by this formula. On the other hand, it's the surface gravity of the black hole, and they turned out to be the same. And now, since they are the same, this relation is the same as the Hawking relation between temperature and surface gravity. But most many body systems do not obey this relation. Kappa which is just the growth exponent, because these are not gravitational systems, is much smaller than 2 pi t. So one can try to saturate the Stanford-Schenker-Moldacena band by using various models. And this is one attempt which failed. I actually tried this model first. It's the Heisenberg model with random interactions. So there are spins, quantum spins that interact with each other, and the coupling constants are random. These are random Gaussian variables. Each pair of spins has a small interaction between them. If this interaction was positive, then the system would align and make a ferromagnet. If it were negative, then it would be more complex. But if it's random, then most likely it will be some uncorrelated system. But it so happens that at high temperature, the system is paramagnetic, no magnetic ordering, and one can calculate the out-of-time order correlators, at least estimate them, and the growth exponent will be proportional to the coupling, and high temperature means that the coupling is much smaller than the temperature. So we're not going to saturate the Stanford Schenker-Moldacena band. At low temperatures, the system freezes to a spin glass, and these out-of-time orders are hard to calculate. It's very unlikely that it will behave in the right way. One can also try other systems. For example, the random Hubbard system, random Hubbard model. And in this model and many other models, there are two regimes that are very easy to achieve. At low temperature, the system either forms an ordered state, ferromagnet or antiferromagnet or spin glass or something else, or it becomes weakly interacting, like a Fermi liquid. And one needs a system that is strongly correlated at low temperature and doesn't form an ordered state. And such a model was proposed by Sachdie-Finier in 1993, and their motivation was similar in the sense that they also looked for strongly correlated systems. They were interested in high-temperature superconductivity. And they found a model using SUM spins. M is a large number, but their model had two parameters, M and N. And this model has only one parameter, N. So we have N Majorana modes that talk with each other. They interact using the quartic interaction. And the coupling constant between each combination of 4 Majoranas is proportional to n to the minus 3. This is to make a good thermodynamic limit. And in this thermodynamic limit, the green function, which is the correlator of Majorana apparatus in time, tau is the imaginary time, doesn't scale with n. What is special about this model? It's strongly correlated at low temperatures. Low temperatures means that beta, the inverse temperature, times J is much greater than 1. It's not a Fermi liquid, not a spin glass. It's exactly solvable using the dynamic mean field. And a complete analytic solution, not even using a computer, in this is possible in this regime. Beta J is between n, which is large, and 1. This model has emergent symmetries, and it has an emergent diffeomorphism symmetry, diffeomorphism of the circle that is broken to PSL to R. And now, in the last 10 minutes, I'll try to explain some details of this model. Not much detail. First, why it is solvable. What is the dynamic mean field? The dynamic mean field is a simple procedure where we reduce the effect of many interactions to some simple quantities. And here the simplifying assumption is that each spin simultaneously interacts with many spins, and those interactions add up in a random way. So we can define a local field that acts on spin j. It's not a spin, it's a Majorana amount actually. It's a sum of many terms. Each term is cubic in the other Majorana amounts. This operator O is a Gaussian variable because it's a sum of many random contributions. Those numbers j are random. And if we know the correlation function between chi sub k at different times, even though chi is not Gaussian, we can find the correlation function for the O field, and that will be Gaussian. So we can assume that there are some correlation functions for the chi fields and some correlations for the O fields. The sigma, the correlation for the O fields, is just the chi correlator cube, because there are 3 Majoranas here. And the second equation, it's the Schrödinger-Dyson equation, follows if we just consider the evolution of a single chi field, a single Majorana, in a Gaussian random field fluctuating in time. That will make the second equation. So it's a closed system of equations. It can be solved, but this system has a symmetry that occurs at low temperatures. If we neglect this, if we neglect this very last thing, G naught to the -1, which may be neglected when the temperature is small and beta J is big. If we do that, then any solution is equivalent to another solution of this form, and f is an arbitrary function. So we can pick one solution that is denoted by J infinity and modify it using function f, and we obtain a new solution. J infinity is just the difference between 2 times raised to some power, which is given by this delta. And f is given by, it's reduced to phi of tau. Phi is a map from the circle to itself. Now, I'm talking about the imaginary time. Imaginary time goes around a circle. It goes from 0 to beta. Beta is the inverse temperature, and then it goes back. So all the solutions are obtained by deformation of a time circle. And now let's make this mental picture. The time circle is like a spring. It's a spring that is made into a circle, and we can deform the spring. It has some rigidity, it has some elastic energy. And if we put the neglected term back, that would give exactly this elastic energy. The energy will depend on the actual function phi. And it depends on phi in a funny way. This is the formula with the short chain. The short chain is a well-known quantity from mathematics. It's defined in this way, and it's related to conformal transformations and many other things. So the effective action has some coefficient that is proportional to the specific heat of the system and this short chain. So it's a formal transformation. We begin with a system of fermions, identify some collective mode, and a collective mode could be, for example, a sound wave. It's more common in conventional many-body system, but here it's this spring on a circle. This is the collective mode. And we can relate this effective action to other models which have the same effective action. If we take the hyperbolic plane, I'm using the Poincare disk model of the hyperbolic plane. It's a curved space, negatively curved two-dimensional space. A sphere is a positively curved two-dimensional space, but one can also make a negatively curved one. And one can draw a curve in this sphere. Suppose that this curve has a constant length, but its energy depends on the area. And this is similar to making a balloon, although it's a two-dimensional balloon. It's a balloon in the hyperbolic plane. There is a shell of that balloon, that green curve, and some pressure inside. And at equilibrium, it will form a circle, but this circle can fluctuate. And we're interested in the thermal fluctuations of that circle. So this is a problem of statistical mechanics. It is defined using the imaginary time. The imaginary time is basically the length of this curve. If we transform this problem to Lorentzian time, Lorentzian space-time, then the curve becomes a particle walled line in space-time. And now, I haven't showed it in the picture, but you can imagine a vertical strip, and there are two particles traveling in time on one side, another particle on the other side. These are particle walled lines, and those particles are on the opposite side of a black hole horizon. This space in between those particles is actually a black hole geometry. So this problem is related to a fluctuating boundary of space that encloses a black hole. One can say it the other way around. If the boundary is fixed, it's the fluctuation of the black hole horizon that is described by the model. And that's why this model is related to the black hole. It's a two-dimensional black hole, actually. Okay, this is a summary. We found a model, this SYK model, that is similar to a two-dimensional black hole. And in particular, they have the same growth rate for the out-of-time order correlators. It's just one collective mode in the fermionic system. There are other modes which are not so easily described by an effective theory. Can one make an exact correspondence between those other modes and some excitations in the two-dimensional bulk? The two-dimensional bulk is actually in so-called anti-de Sitter space. It's basically the Lorentzian analog of the hyperbolic plane. I don't know, but hopefully there is a one-to-one correspondence. But on the other hand, this correspondence might be contrived, because to make it, one might have to introduce an infinite set of parameters for the bulk theory. And finally, what about the black hole information paradox? That was the original motivation of this work. I still don't know the answer. So I'm still working on it. Yeah, you can work on that too. Yeah, thank you.
Questions? Yes.
Okay, so which models which saturate the bound for the nothing of exponent. So this might be the simplest, but for example, the other one, the CalTech model, that was for large M, because for M equals 2, it doesn't saturate,
Yeah, that was for large M.
M has to be large.
Yeah, that's right.
And do you have any general kind of rough test of What do you have in the model?
I think their model for any finite M would form a spin glass at low temperatures. So it won't saturate the band. The large M model will have almost the same properties if we don't consider 1 over n effects. I don't have a good answer. Yeah, it's a very interesting question, but we just need to find some other examples.
Case by case?
Yeah.
Also, maybe, I can still want another question. This emergent symmetry again, do you have any understanding of why that happens? The reparametrization symmetry.
Mm-hmm.
It does not often happen in the theories at the critical point. You don't have reparametrization symmetry.
Yeah. It's still a mystery to me. I don't know, but I guess this problem is special because it's zero-dimensional. High-dimensional problems are more rigid. Maybe that's why.
Other, like the competing model for a black hole in simplicity is the so-called matrix model C for 1. Again, it's zero-dimensional.
Yeah.
But it doesn't have these features.
Yeah, that's right.
It doesn't have the emergent reparametrization symmetry. So it is very special. I'm not sure that any other zero-dimensional model, it's not clear it has symmetry. At this point, it's only one model which has it.
Yeah. There are some variations like supersymmetric versions. Yeah. Yeah, I agree.
So you told us how you can shed light on the physics of black holes starting with a model of disordered material. So I wonder if it's possible to go in the opposite direction, get some knowledge about disordered condensed matter systems from black holes.
Yeah, I guess Subert-Sachdev would give a better answer. His idea was that such models that are similar to black holes describe a high TC superconductor. And I could give my motivation. It might be slightly different from Subert's explanation. In a high TC superconductor, there is a small, relatively small fraction of electrons that contribute to the effect that are near the corners of the spectrum where the density of states is high. And suppose that there are random interactions between those electrons. If we project those random interactions onto a small subspace, then we'll get almost random terms. And it's sort of similar. We have random quartic interactions on a system where a quadratic interaction is non-zero but still small. So this might show some way to apply this theory.
Okay, so if there are no further questions, let us thank the speaker again.